So I'm going to share my screen now and begin my talk. Is that right?
Yes, that's right.
Okay, very good. So can you see my screen and hear me okay?
Yes, we can see your screen, and I guess we can hear you fine.
Yeah, if there's any difficulty, just stop me and let me know. So hi, my name is Sheila McIlraith, and I'm going to talk about formal languages, help agents learn and reason. So before I start, I wanted to acknowledge the collaborators and the people who worked on the material that I'm going to present today. So much of the material I'm going to present is Rodrigo Toro Acarta's PhD thesis work. He was a PhD student of mine at the University of Toronto, and now he's an assistant professor at the Catholic University in Santiago, Chile. And this work was done in collaboration with Torin Klassen and Rick Valenzano, most of it, who were at the University of Toronto. Torin is now a postdoc at the University of Toronto, and Rick was and now is on faculty at Toronto Metropolitan University. Alberto Camacho was also involved in some related work, as were some of the people that I'm showing here on my slide. So I want to start by talking about language. Humans have evolved language over tens of thousands of years to provide useful abstractions for understanding and interacting with each other and with the physical world. The claim advanced by some is that language influences what we think, what we perceive, how we focus our attention, and what we remember. We use language to capture our understanding of the world around us, to communicate high-level goals, intentions, and objectives, and to support coordination with others. I think what's really important about language is that in computer science and in the study of AI, we use knowledge representation languages and programming languages to capture our understanding of the world and to communicate unambiguously with computers. Importantly, language provides us with useful and purposeful abstractions that can help us to generalize and transfer knowledge to new situations. So the question that I want to explore today in this talk is, can exploiting the alphabet and structure of language help AI agents learn and reason? Can we use that natural compositional structure to really
Sheila,
learn?
can you please give me a minute? I'm trying to...
Yep, I'll pause.
Sheila, can you give me a minute? There are some audio issues that I am trying to resolve.
Very good.
Can you hear me, Sheila?
You're a little scratchy, but I can hear you.
Yeah, now you can share the slide, and I think it should be okay now.
Should I carry on from where I was, or should I start again?
You can carry on from where you were.
Okay. Actually, let me just... So as I mentioned, the question that I want to explore here is, can exploiting the alphabet and structure of language help AI agents learn and reason? So in particular, if we imagine just to ground this in a particular scenario, imagine that you have a robot that you brought into your home, and the robot has particular skills. It knows how to do household chores and help around the house and do various things within the home. It has some knowledge of the home, but still, just like a human being that we might hire to come into our home, we really want to be able to personalize advise, instruct, and task that agent, that robot, or that human being, and to impart knowledge to them about any additional information about our environment. So how do we actually advise, instruct, task, and impart knowledge to our AI agent? And how does an AI utilize this knowledge to learn and to act? Those are some of the questions that we're going to explore today. So we're going to do this in the context of reinforcement learning. So just as a very quick overview of reinforcement learning, of course, reinforcement learning is used for sequential decision-making, for planning. And in this formulation, we do not have a model of the environment, of the dynamics of the environment, like we would in a regular symbolic planning setting, for example. So the agent has a set of actions that it knows that it can execute, and but it doesn't know the outcomes of those actions. So it's like walking blindly. The agent performs an action, and the environment tells it what state it's in as a result of that action, and also any sort of reward that it gets, that it garners from the environment. And using that type of information through some trial and error or curriculum-based set of experiences that the agent does. The agent interacts with the environment over and over and over again, and collecting these experiences, these states and rewards as a function of the actions it's performed. And its objective is to learn a policy, a mapping from states to actions or action distributions that optimizes its expected cumulative reward. So the problem is, though, when we think about this in the context of actually trying to task an agent to do something in the environment, the only sort of signal that we're able to give that agent is through the reward function, or that's the typical place where we do it. And a reward function in some ways is very impoverished. It's just a function that maps the state into a real number, or a state action successor state into a real number. So if you're playing some sort of a game, maybe minus 1,000 if you hit a bomb, and plus 1,100 if you pick up the gold, and so on. So two challenges to reinforcement learning in the real world are reward specification, that it's really hard to define reward functions for complex tasks and for complex behavior, which is a lot of the type of behavior that we're actually interested in. And of course, as some of you, if you're graduate students in the audience, know, you're often the ones who get stuck writing some Python program that takes some aspirational behavior and tries to find some mapping from the state of the system into that very complex behavior, and a reward function that rewards it suitably so that the behavior is manifest appropriately. So that's one problem. The second big problem is sample efficiency. Reinforcement learning agents require billions of interactions with the environment to learn good policies. As you can imagine, you close your eyes and walk around in the dark, and it takes a long time to figure out what you need to do to perform some sort of a complex task, even with some sort of reward. So returning to this particular scenario that I described, particularly with the robot, I wanted to just show you a couple of examples of the types of rewards that one might wish to, or reward-worthy behavior that one might wish to describe to an agent. So there are all sorts of things that fall under the basic definition of a reward function that we want to stuff into the reward function. Those could be goals, preferences, norms, or laws. So for example, run the dishwasher when it's full or when dishes are needed for the next meal. Make sure the bath temperature is between 38 and 43 Celsius immediately before letting someone enter the bathtub. Do not vacuum while someone in the house is sleeping. Or in Canada, in Quebec only, if you're driving in Quebec, never turn right on a red light. That's very important, because if you do, you'll get a big fat ticket. In another type of what's important about these is that many of them are temporally extended. They're not just about the state or the state action successor state, but they're behaviors that extend over a period of time. They're also conditional, and they have all sorts of interesting conjunctive or disjunct, can have interesting conjunctive or disjunctive behavior. Just to bring that home a little bit more, I wanted to give you an example of an instruction. When assisting someone from a car to the sidewalk, please always open the car door closest to the person, help the person to standing, move them beyond the car door, close the door, and then walk them to the sidewalk. Pretty straightforward, and it seems like it's just a sequence of actions, no particular complex structure. But what's important about this instruction, as with all instructions, is it's great if you finish it all, but finishing half of this sequence of instructions should not garner you half of the reward, because if you get some person out of the taxi to escort them to the hospital, and you leave them with the door open in the middle of the road, that you should not get half of the reward. You should get minus 1,000, because you're leaving this person in a very endangered situation. And so the important thing about instructions is that they really need to be completed in order to garner reward, and finishing half of them should not garner half of the behavior, or half of the reward of the entire instruction set. So all of these things, goals, preferences, norms, laws, and instructions really require some careful thought as to how they're treated. So how do we communicate this to our reinforcement learning agent? I've described these things to you in English, but how do we actually describe them to a reinforcement learning agent? So it is the case, and I think ChatGPT and all the large language models that we've been seeing over the last year really bring home the fact that eventually we would really like to communicate with our AI agents using natural language, using whatever our native language is. But there are cases, just as with computer programming, where we want to be precise, safety critical situations where we cannot afford to humor the ambiguities of, for example, the English language or another natural language, where we really need to be precise. And in those cases, there really is an appeal to using formal languages. And so that's what I'm going to talk about today. And my contention is that the alphabet, compositional syntax, and semantics of formal languages, but all languages really, can help reinforcement learning agents learn what to remember, and to reason. So before I launch into talking about the use of formal languages and how to exploit its compositional structure, I wanted to just pause for a minute and extol some of the virtues of formal language. So first and foremost, formal languages have a well-defined syntax and semantics. They are unambiguously interpretable by computers, which is a really important property, which is why we use them as programming languages, for example. There are also many languages are parsimonious. And so just there's a notion of what I tell you explicitly, but in that those explicit things, there are often a lot of implicit things that can be extracted using some form of inference. And of course, in knowledge representation, that's something that we do all the time using theorem proving or some sort of other systematic proof procedure. But I wanted to illustrate it first in just with a set of linear equations. So x plus y equals z, plus z equals 18, z minus x equals 7, 5 minus y equals 0. Those are three things that I've written down explicitly, but implicit in there is that x equals 3, y equals 5, and z equals 10. We can perform some sort of systematic manipulation of those sentences and produce some more information that is actually embedded or implicit in that representation. If we were to use logic instead, and I told you A implies B and A, what would be implicit in there would be B. And of course, we can use some sound inference procedure to extract what is true, what is inferred by those logical statements. These are very simple examples, but of course, it's important to look more generally. If we use first order logic, unnamed individuals are very important. There exists an X such that person X and in room X 12,000. I can do all sorts of reasoning about the person who's in room 12,000 without ever mentioning them, without ever saying that it's Sheila or it's Asim or it's somebody else. Maybe I never need to mention or identify the person. It's just, I can talk about objects by their properties. And that's a very powerful thing to be able to do. I can also do, in the other direction, you can use typing and generalization to take individuals that we know about and to talk about them as a collective and not to have to enumerate properties of them as an individual. So for example, I had 450 students in my Intro to AI class last year, and for all X, enrolled X in CSC 384, which is our Intro to AI course, has test X Monday. So all of my students had tests on Monday. I didn't want to write it out 450 times, but I can write it out parsimoniously using first order logic. Perhaps one of the most important things I think about logic, for example, as a formal language, is that it can represent incomplete information very effectively. So we always, our descriptions of the world, our understanding of the world for each of us is incomplete. What we observe in the world at any moment in time is incomplete. We can write those things down using a formal language, such as propositional logic, which I'm using here. And that those finite set of sentences induce a set of models or a set of interpretations that describe many different ways the world can be. So using the example that I have on the left, A implies B, and A tells me that A is true and B is true in every way the world can be. But C or D tells me that C can be true and D can be false, C can be false, D can be true, or they can both be true, which induces three different ways the world can be, as we can see in that truth table representation on the right. But if we're dealing with first order logic, then a finite set of sentences can actually describe an infinite number of different worlds, an infinite number of different ways the world can be, and we can manipulate and reason about those infinite worlds by simply manipulating the sentences of the language, which is a very powerful concept. It's also the case that we can do compositional and lazy evaluation. A and B and C is false as soon as one proposition is false. We don't have to evaluate them all. Similarly, A or B or C is true as soon as one proposition is true. And if we've got a million of them, we don't have to evaluate them all. We only have to evaluate one. And so that's a very powerful technique, especially when we're dealing with incomplete or noisy information. We can do efficient search. This is an example I used to use in my class. I used to teach Prolog a number of years ago. If I was trying to find my American cousins, I wouldn't go out and list the 340 million Americans and test whether each one was my cousin. If I only had, let's say I had 10 cousins, rather I'd find my 10 cousins and then check to see whether they're American. So you can order things and do very efficient search, and you can reason about those types of properties. Finally, formal languages and automata can be generators and recognizers of language, and that's a very important property that we're going to exploit today in this talk. So returning to the question that I asked before, how do we advise, instruct, task, and impart knowledge to our AI? We're going to use formal language, and in particular, I'm going to motivate this in terms of linear temporal logic because we've done a lot of work in that area. Linear temporal logic is a modal temporal, a propositional modal logic that describes properties of traces. So properties of repeated sets of a sequence of states. It's used in, I suspect many of you are familiar with it. It's used in formal verification to talk about properties of the execution of programs or properties of hardware systems that one wants to ensure are enforced by the execution of a program or by the execution or by the execution of a piece of hardware. And so they're and it has a very compelling syntax that is English-like in many ways. It talks about next, eventually, until, always have $5 in my pocket, always have my keys in my pocket, eventually be at home or eventually eat dinner, always eventually get a job, and so on and so forth. We write down a set of properties in terms of a set of formulae, and they're interpreted over either finite traces, so finite episodes, or over infinite traces, such as what you might want to do with a controller that runs forever and ever and ever. Importantly, any set of formulae, a conjunction of formulae or a set of formulae, can be transformed into an automata representation. And I want you to remember that because it's a very important aspect of my talk. So just to give you a very simple example, do not vacuum while someone is sleeping, which is a property that you might want to give to your robot in your home. We can imagine that we have two propositions, vacuum and sleeping, each of which is true when vacuum is occurring and sleeping is occurring. And we would write a formula that says always not vacuum and sleeping, so that vacuum and sleeping are true at the same time. And of course, we typically would use the box notation, which is it, or G and F. There are various ways, syntaxes that are used for always and eventually in linear temporal logic, but this is the canonical one. So that's great. You can imagine, sort of going back to those examples that I gave you before, and imagine writing them in linear temporal logic. So now I know how to write some of these things in a formal language, but how am I going to communicate these to a reinforcement learning agent? Remember, we've just got that function, R of S goes to some real number, or R of S prime goes to some real number. So what's the next step in this process? And the answer is automata. I'm going to write those reward-worthy behaviors as and in linear temporal logic or directly in automata, and I'm going to use those for reinforcement learning. So just to sort of give you a sense of why automata are very important, this is just a sort of 101. Maybe some of you remember this from an automata, a formal language course you took as an undergraduate. But the picture on the right is Noam Chomsky, and the diagram on the left is what's referred to as a Chomsky hierarchy, which is a hierarchy of increasingly expressive languages that go all the way up to type 0 languages, which are unrestricted languages, which are equivalent to Turing machines. But at the bottom, the type 3 languages are the regular languages, and they can be represented as finite state automata. And those are things like, Kleene star, sequence, and again, some of the macros, if then else while loops. Typical procedural programming languages that don't have subroutines in them are regular languages, and many variants of linear temporal logic can also be represented as finite state automata. As we go up the hierarchy, we need memory or various other things, so we go to push down automata and so on. But the message is that again, subsets of natural language and many languages can be represented in all sorts of different types of automata, and we are going to use those in our reinforcement learning, and in particular in something that I'm going to call a reward machine that I'm going to talk to you about now. So for the rest of the talk, I'm going to tell you a little bit about reward machines, how to exploit their structure in learning, and tell you some great experiments that we've run and how to create them. So I'm going to start with an example. What you see on the left is a very simple grid world domain. It has a little agent that's this triangle here, and it has 4 locations, A, B, C, and D. It has 2 coffee stations, very important, a mailroom, and also an office. And the task that we want the agent to perform is to go from A to B to C to D. Now, the problem with this example is that it's non-Markovian. We don't see when the agent is at A, when we see the agent on the screen right now, and this is what we would see in the state, we don't know where it's been before. And so to perform the patrolling task, one has to remember where it's been before. So how do we go about doing this? Well, what would typically happen is that you would write a program, a Python program that would take a counter and keep track of where you were going and compute the reward that way. And here's a very simple way of doing it on the right. What we're advocating for here is to define a reward function using a reward machine. So what we would do is take the Python code and instead write it in an automata-like structure that I'm going to tell you about and describe in further detail in the next slide. But it's over a set of a vocabulary, which is a set of propositions. Here, whether you're at the coffee machine, whether you're at the mailroom, whether you're at the office, whether you've hit these stars, which are little pieces of little furnitures that you don't want to hit at location A, B, C, or D. So a reward machine is an automata structure that's comprised of a finite set of states, U, here, U0, U1, U2, U3, which is describing this patrolling task, an initial state, U0, a set of transitions, and here in this sort of simplified version that I'm describing to you in this talk, the labeling is a logical condition or a guard, and also a reward function. So for example, when I'm in U0, I start in U0 and until I get to remember I want to go to A, B, C, D, and then I'm going to get a reward. for one loop of the patrol, and then I'm going to continue on and on. And what I see here is that once I hit A, I get a reward of 0, and I transition to U1. And once I stay here, while B is false, when I get to B, I transition to U2, and so on. What's interesting here is that here this is what we refer to as a simple reward function. So the rewards are just a scalar number, but instead we can actually have quite complex functions on these links that transition between the states. So a reward machine, here's a very simple example of a reward machine in action. Watch the little purple guy go, our little agent, there it is. And it stays in U0 because it hasn't gotten to A yet, and it gets a reward of 0. When it gets to A, it tells the reward machine, it transitions to U1, but it still gets a reward of 0, and so on. When it stays in the same state until it gets to B, and then to skip a few, when it finally goes from A to B to C, it will be in U3, and when it moves to D, having gone to A, B, and C, it will again transition back to U0, but it will get a reward of 1 because that is what the function says. So here are some other examples. Deliver coffee to the office while avoiding furniture. So coffee and star, which is the furniture. So I get coffee and then I go to the office without hitting the furniture, and I get into U3 and I get a reward of 1. But as soon as I hit the furniture, I go into a sync state while which I stay at forever and can never get any reward This is a typical example of a safety condition. Here, the safety condition is to not hit the furniture, but you can imagine a more consequential type of safety condition that we might want to be able to enforce. Another example, deliver coffee and mail to the office. I want to do it in either order. I haven't specified, so I can do coffee, mail, and then go to the office, or I can do mail, coffee, and then go to the office. These reward functions are actually, these reward machines and these automata structures are as expressive as a regular language. So they're very expressive. They can express everything that was in that Python code and that we saw at simple Python code and much more. So hopefully I've convinced you that we've done a lot of work in reinforcement learning with linear temporal logic proper. I'm talking about automata today, but I hope that I've convinced you that these languages and their relationships to automata provide a very rich language for expressing complex temporally extended behavior. But remember, my premise was that we can exploit the syntax and semantics of these formal languages in order to learn and remember. And so I want to talk about that next. And in particular, I want to talk about how we learn with these automata structures. So exploiting reward machine structure in learning. Our approach is based on a very simple idea. It's such an obvious idea. I don't know why more people don't use it, which is the notion that someone always has to program the reward function. So you and I are wired for pleasure and pain. We get, I get plus 100 when I eat ice cream, and I get minus 20 when I stub my toe. But an agent, an AI that we build is not built that way. It's not a biological system any reward that it gets has to be programmed implicitly or explicitly by somebody, even when it's interacting with the real environment. There has to be some notion of the program of the reward function defined by a human being. And so so we currently treat that reward function as a black box where we just ask for what the value is that we're getting back. But why not treat it as a glass box? In particular, the simple idea is to give the agent access to the reward function and exploit that reward function structure in learning. And that's exactly what we're going to do. So the agent can actually exploit that reward function structure in learning. I'm going to go very quickly. We've got a number of different techniques that we've developed to exploit that structure. I'm going to show you a simple baseline, and then I'm going to show you an algorithm that we've used that has been very effective and some elaborations, and then I'll go to our experimental results. So the obvious thing to do is Q learning over the cross-product MDP and reward machine, and that's going to be one of our baselines. I'll just mention this quickly to you. So we want to use Q learning, a simple way of learning the Q value, the value of a particular state and action. And a reward, but the problem is that a reward machine, as we've seen, may define a non-Markovian reward function. I'll mention to you, I'll explain to you what exactly I mean by that. And that's that the reward doesn't just depend on the current state, but it depends on the state history. It's non-Markovian. It's not Markov with respect to the current state. And so just to illustrate that, or to ground that for you, if I had started in the square just to the left of A, and I'd gone to A, but then I'd immediately moved to where the little purple triangle is now, which is just to the left of D. And then I'd be in U1 because I would have started in U0. I would have gone to A, and I'd be in U1 in my reward machine. And if I moved to D, I would get a reward of 0. However, if I were in that exact same state, the state just to the left of D, and that's all we know what state the agent is in, but I had, in the past, I had gone to A, then B, then C, then D, then my reward machine would have registered that I was in U3, not in U1 as I was before. And so when I did that same move from to the left of D to D, so same action from the same state, this time I'm going to get a reward of 1, even though when I performed that other action, the other time, I got a reward of 0. So the reward machine may depend on a non-Markovian reward function. It depended on the history. And so an obvious thing to do is to actually take the typical, the typical agent state and augment it with this information that's in the reward machine to do the cross product of the automaton with the state of the system. And indeed, that was our baseline. And as you're going to see, it doesn't, it seems like that should be enough, but it doesn't work very well compared to what we've done. And so we also did some very interesting work on hierarchical reinforcement learning. I'm not going to talk about it, but I'll show you for time. You can see it in our papers, or you can, but I'll show you some of the experimental results. What I really want to talk about is our algorithm QRM, which is Q learning for reward machines. And here's how it works. So we have our reward machine on the right, and we learn one policy or Q value function per state in the reward machine. So for U0, we learn a Q value function Q0. In U1, we learn Q1. In U2, we learn Q2, and so on. We're going to select actions using the policy of the current reward machine state. And then, so in U0, we'll use Q0. In U1, we'll use Q1. In U2, we'll use Q2. And then we're going to reuse experience to update all the Q values of all the different functions using off-policy reinforcement learning. And this is really important to remember. It's a form of counterfactual reasoning. It's similar to hindsight experience replay in some conceptual way, for those of you who know something about that. And I'm just going to show you quickly how that works. So if I'm in U0, and I take a move, I'm going to update each Q function as if the reward machine were in the corresponding state. So if I move from the left of D to D and I'm in U0, I'll get a reward of 0, and I'll update my Q function at 0, my Q0 Q function. So I'll have my immediate reward, the reward I got in the state, plus the discounted future reward that I'm going to get in the successor state that I'm going to be in, which is going to be S prime, A prime. If I'm instead in U1, I'll similarly get Q, but counterfactually, if I wasn't, even though I'm really in U0, if counterfactually I imagine in my head that I was instead in U1, then I can similarly update the function. And if I'm in U2, I can similarly update the function. If I'm in Q2, I still get a 0 if I move to D, and I again will update the function will be the expected, the maximum future reward that I'm going to get. However, if I'm in U3, again counterfactually, I will get, if I make that move from the left of D to D, as we know it from where we saw before, what's going to happen is that I'm going to get a reward of 1, and I'm going to transition to U0. So that transition tells me that the update is for Q3 is 1 plus the discounted future return, which is going to be the max of Q0. So I can also, that's QRM, and very quickly, it's Q learning with this counterfactual reasoning for each state. I can augment it with reward shaping, which is for those of you who know something about reinforcement learning, is a way of dealing with sparse rewards by basically taking a cookie that you might get at the end of some long behavior that you perform and breaking it apart to sort of crumble it along the pathway so that you get that there's more of a path for the agent to follow. That's sort of conceptually what it does, but what it does mathematically is it's a beautiful work by Andrew Ng and Harada and Russell from a long time ago, from 1999, I think, where they defined these potential functions that were just rewritings of the reward function that preserve the optimality of the Q learning algorithm. And we can do the same thing here for reinforcement learning by treating the reward machine as an MDP, performing value iteration over that reward machine, and then applying the QRM algorithm. And you can see the reshaped reward machine down here just to give you a sense of what it might look like. It's just adding a little bit of cookie here and taking a little bit of cookie away somewhere else. So a final algorithm that I just want to mention that I'm not going to talk about today, but for those who are interested, you can look at our papers. We've, in addition to QRM, we've also defined something called CRM. So QRM has, and the distinction between the two is as follows. QRM uses multiple Q functions. So there's one Q function, Q of SA, per state in the reward machine. Per each one of these states, each has a Q function associated with it. In contrast, CRM only has one Q function because the reward machine state is actually part of the function itself. So we take the cross product of SU and define the Q function that way. And then we synthesize, as we did, and as I showed you with QRM, we can synthesize counterfactual experiences for all of the states SUI, just as we did similarly with CRM. So the advantage of this is that it's much easier to integrate this type of a function into a deep learning algorithm without actually having to rewrite it extensively, because there's only one Q function that you're learning. And CRM, and I'll note that as might meet with your intuition, CRM behaves identically to QRM in tabular domains. So an important property of QRM and CRM with reward shaping is the following: that QRM and CRM, with and without reward shaping, preserve the optimality guarantees of Q learning and reward shaping. And that means that for tabular settings where we don't have function approximation, they converge to optimal policies when there's no function approximation. So that's a really exciting result. So now I'd like to tell you about some experiments. So we tested in discrete domains, and I'm going to show you a subset of some of our experiments: Q learning in the cross product, hierarchical reinforcement learning with and without a reward machine, QRM and QRM with reward shaping. And note that they are, again, apropos the theorem that I just showed you, they are all guaranteed to be optimal in these tabular domains, and everything except the original Q learning uses some form of decomposition. So let's see how it works. We have on the left, our office world environment, and we did 4 tasks, 30 independent trials per task in this environment. And on the right, I'm going to show you the results. On the y-axis is the discounted reward. So we just recompute, we normalize the normalized discounted reward. So we normalize the reward. So 1 is perfect. And on the x-axis is the number of training steps. And here it goes from 0 to 50,000 for these simpler examples. And I'm going to show you the results for 4 different algorithms. So what you'll notice, our algorithm to hit the punchline first is QRM, which is the red line, which you can see very quickly with a small number of training steps converges to the optimal solution. Whereas Q learning with the cross-product reward machine, which should work better than just plain old Q learning, is still, after 50,000 steps, not even just maybe halfway towards converging to the optimal. But remember, it is guaranteed to converge to the optimal in the limit. So somewhere out here off of the page, it will eventually get up to that 1 because of that it's guaranteed to do so. But it's not very sample efficient. Remember, sample efficiency and expressiveness were 2 real challenges to to reinforcement learning in practice. In the middle, we will see hierarchical. The yellow is hierarchical reinforcement learning, and the blue, the sort of turquoisey blue, is hierarchical reinforcement learning with reward machines, where we actually use the reward state to help the microcontroller of the hierarchical reinforcement learning system choose which policy to enact, which skill to use to to invoke its solution. So the reason it doesn't do as well, because hierarchical reinforcement learning is actually very good, is because it's myopic in terms of its search. And so it plateaus at a suboptimal solution. And I'll explain to you why that is in the next slide here. So
Sheila, can I request to finish in 5 to 10 minutes?
Yes.
5, 7.
Yep, very good. Thank you for the time. I know we had shorter for this the audience. Asim just told me before I got on that I had a little bit less time than originally planned because there was some reworking. So I'm just going to shorten some things at the end as a consequence, but no problem at all. So hierarchical reinforcement learning always chooses the myopic solution. So the best solution, if for an agent to get coffee and go to the office, is to take a long step to the farther coffee, after which the office is very close. But hierarchical reinforcement learning won't do that. It will myopically choose the close coffee machine, relegating it then to have to take this very long route to get to the office, which is why in these results you'll see that it's often manifests suboptimal behavior. So anyways, we did craft world domains. We see the same phenomenon. Again, here's our QRM algorithm, which is converging to the optimal solution with very low sample size. The 2 hierarchical reinforcement learning techniques that plateau that also do very well for sample efficiency, but plateau to suboptimal solutions. And the cross product Q learning, which is down here at the bottom, is still flatlined. And I will remind you again that it is guaranteed to converge to optimal given enough training steps. So again, it speaks to the effectiveness of this solution. In continuous spaces, this is a water world domain. It's like playing billiards or pool. We're controlling the white ball, and we gave it instructions like hit 2 red balls and then a yellow ball, or never hit any purple balls. And again, in this deep learning environment, we saw that where we replaced Q learning with double DQN, these were results that were done in 2018. We've got some more modern ones that I'll show you at the end. It did much better. So again, we show our superior performance. We're in red relative to the Q learning baseline and the 2 hierarchical techniques in the middle. For CRM, we did some which is the new version of the algorithm where we have not individual Q functions, but one big Q function. We did very well on half-cheetah domains. This is us in orange with CRM and the hierarchical reinforcement learning algorithm in this environment. But again, where optimality doesn't matter, or where being myopic, as hierarchical reinforcement learning is, doesn't affect the particular task, where you're just going 1, 2, 3, 4, 5 to one state and the other, which is what we did with this cheated task on the right. Hierarchical reinforcement learning actually does a little bit better. So I want to I'll mention a couple of things really quickly, and then I'll wrap up. So I think a question you might ask yourself is, gee, do I have to write these automata? Where do these reward machines come from? And indeed, you can write automata. And maybe for those of us here, if we're all computer scientists, it might be easy to write simple automata. But there are many other ways in which we can create reward machines. And just very quickly, we can specify them, we can generate them, and we can learn them. And we've done some work on each of those. And the beautiful thing is that because automata are this uniform normal form representation of all sorts of different, that capture the syntax of all sorts of different languages in a uniform structure, we can specify in any combinations of different properties. Some things will be more naturally expressed in procedural programming languages. Some things will be more naturally expressed in LTL. We can represent them as a DFA, as a deterministic finite state automata, translate them to a reward machine, and then use these our tailored algorithms or some that somebody else creates in the future, without having to write a new algorithm or for every representation, every language that we want to use. So the automata really provide this beautiful normal form structure. We can learn these things through high-level symbolic planning, where we generate a set of instructions, or we can use a large language model to generate the instructions, and then use an automata and then rewrite them as a reward machine, as we've done in some of our work. And we can also learn them. I'm not going to be able to talk to you about this, and we can use them as memory. This is very interesting work that perhaps you can read about on your own sometime. So just wrapping up, I'll move ahead. There's an example of a reward machine that we learned that acts as memory in this partially observable environment. Very nice work with great results. So to recap, the question I asked was, how do we advise, instruct, task, and impart knowledge to an AI that learns? I talked about the challenges of reinforcement learning, reward specification, and sample efficiency. And my claim was that the alphabet and compositional syntax and semantics of formal languages, but really any languages, can help reinforcement learning agents learn what to remember, and reason. And that formal language is a powerful and effective tool to advise, instruct, task, and impart knowledge to an AI. The big idea was this notion of defining a reward machine. And the key insight was to reveal the reward function to the agent, so that it could use its structure, its syntactic structure, to learn more efficiently. And we had great results. And there's lots of code. There are lots of papers. We've done some interesting work with linear temporal logic as well as automata. And and as well as some work with linear temporal logic and automata, where we do have models, because of course and again, exploiting these same types of notions. So that's it. Thank you very much. And sorry, this was a little bit shorter than planned, but hopefully you got something out of it and the main ideas. So thank you for listening.
Thank you, Sheila. So we have time for one question. Yeah, please. Yeah, you have to come here. Sorry. And just stand here, look at the screen, and then stop.
Hello, yeah, thanks for the great talk. And just a quick question. I was wondering, because automata, they accept languages, and I didn't see exactly, do you use the language that the automata accepts as part of the learning process with the reward machines? Or maybe you could just, if you could talk about that a little bit.
So we use the structure. So there are two components. The automata divide the structure, the learning, by identifying a set of individual using the I'll use the QRM algorithm. So they decompose the learning of the reward function into learning Q functions for each of the states of the automata. So I could take any language, translate it into this automata, and it has a set of states. So I learn a Q function for each of the states in the automata. So it's separated that way. Out of the syntax. But then the other part of it, where the syntax of the actual domain is used, is in the condition of the transition between one state to the next. I had very simple, I just had I didn't have a very complex logical condition. I just had A, once you'd hit A, you went to B, but you could have not A and B implies C or D. You could have a very rich formula as that condition that transitions you from one state to another, and thereby have quite a rich structure. But of course, the richness is in the original types of things that I described in English at the beginning, these complex behaviors that can all be written as, for example, linear temporal logic formulae, or maybe they can be written as procedural programs, but they can all be translated into automata of some form using the vocabulary of these propositions that are used. So you definitely are using the syntax and that compositional structure to learn.
Oh, thanks a lot.
Okay, yeah, thank you for the question.
So thank you, Sheila, and with sincere apologies, I forgot to introduce you at the beginning of the talk. Okay.
No problem.
So, but just to briefly, so we were changing the slots and stuff, so I forgot. I sincerely apologize. But Sheila is a professor in the Department of Computer University of Toronto, Canada, CFAR AI Chair, Vector Institute, and an Associate Director and Research Lead at Schwartz Rittman Institute of Technology and Society. And you already saw what she's working on. And she's also fellow of ACM and Association of Advancement of Artificial Intelligence, AAAI. Okay. So thank you so much, Sheila.
Yeah, and thank you for inviting me. I'm sorry I'm not there in person, and it's a great topic. You know, I think composition is really a key. It's something that we've, you know, something we exploit in mathematics all the time, and it's a great topic. So, and in knowledge-based systems as well as in reinforcement learning. So all the best to everyone there, and enjoy the rest of the seminar. For me, it's late, so I'm going to go to sleep. So yeah, so thank you.
Thank you.
Bye.